Hello, my name is Siddhi Sawant and my topic is delay faults in VLSI. Delay faults. Nowadays, transistor size is shrinking and logical circuits are operating at higher frequency to increase the performance. For manufactured circuits to operate correctly, it is essential that the circuit has correct functionality behavior and operates at designated clock period. But due to the shrinking in transistor size and high operating frequency of logic circuits, the manufactured circuits are more vulnerable to manufacturing process, which gives rise to statistical variations of the parameters and to some extent physical defects in integrated circuits. These defects do not alter the logical functionality of the circuit, but they do degrade the circuit performance. These faults are termed as delay faults. Hence, to ensure that the manufactured circuit operates correctly, delay fault testing is an important issue. To maintain test quality for speed-related failures, delay testing is gaining momentum due to growing density and increasing clock rate of chips. The purpose of delay testing is to ensure that whether the circuit operates correctly at the given clock period. A testing methodology which has maximum coverage and minimum cost is needed to be explored. This will ensure that the circuit operates correctly both functionally and timing-wise. The motivation behind this literature survey is to analyze the pros and cons of the different methodologies proposed so far and to compare them. Hence, it is the need of an hour to study this topic in depth and to find a solution which will not hamper the performance of the circuit at higher clocking rates. Different delay fault models are discussed further. Exhaustive model. The size of the transistor is shrinking and number of gates are increased, which gives rise to random defects. Presence of these defects in small number will not hamper the circuit performance at slower clock rates. But at higher clock rates, they degrade the performance of the circuit without altering the circuit functionality. These defects are called delay defects. Exhaustive searching can be used to find these delay faults. The total number of patterns required will be 2 raised to n into 2 raised to n minus 1, where n is the number of inputs. It is feasible for small circuits, but as the value of n increases, it will be time consuming and complex. To overcome the exhaustive search problem, functional delay testing can be used. The properties of n detection functional delay fault test is explored. Using 9 different test generation modes, the functional delay fault tests were built. For detection of gate level transistor, fault tests generated at algorithmic level are suitable. From the results, it was observed that the test sets which are generated according to the functional delay fault model obtain high fault coverage of transition faults. It does overcome the exhaustive search problem, but on the other hand, generating a test for each path delay is time consuming for complex circuits. NI detection test set. To overcome the functional delay testing model, rather than generating a test for each path delay fault, in the proposed method, NI detection test set for single stuck-at faults are used to generate an N propagation test pair. For every transition faults are checkpoints, like primary inputs and fan-out branches, N distinct vector pairs for every transition faults at checkpoints are generated. Further, these N distinct vector pairs are simulated to further determine the effectiveness for robust path delay faults and single testable path delay faults. Practical swarm optimization based algorithm based test generation algorithm. Also, the reduction in size of VLSI circuits has given rise to high capacitive coupling or crosstalk effects. To overcome this problem, particle swarm optimization technique is being proposed. This method can optimize the test vectors to detect the number of crosstalk delay faults. In this methodology, first a random pattern is selected from the population, which consists of search space initially consisting of random patterns. The initial velocity of the test pattern is calculated as shown in the equation. Vij is equal to Vmean plus Vmax minus Vmean into rand, where Vig is the velocity of the ith test vector in the multidimensional search space. Vmax is the maximum velocity, Vmean is the minimum velocity. Rand is the random function which generates a random number. Further, with the selected pattern, the circuit is fault simulated using the crosstalk delay fault simulator for the fault to get propagated to the primary output. At any primary outputs of the fault circuit, if the delay effect is observed and the delay fault is detected, the value of fitness function is evaluated. Using the pseudocode which updates the value of P best for the test pattern is calculated depending upon the fitness value of the previous and current generations. Also, G best, that is the best value obtained so far by any test vector in the neighborhood of that vector, is computed using pseudocode. The position and velocity of each particle is updated using the following equation, as shown in the slide, where Vij is the velocity, Xij is the position of the jth dimension of the ith test vector, P best is the best previous position of the jth test vector, G best is the global best vector, and C1 and C2 are acceleration constant. This process is repeated for all the patterns in the test set. The optimum solution has high fault coverage consisting of minimum number of test vectors. The fitness function for this methodology is equal to number of faults detected. PSO is one of the best algorithms to tackle the optimization of the test suite. Better results for both sequential and combinational circuits are obtained using this algorithm. Effects of periodic testing. Even though the PSO is one of the best algorithms, periodic testing of VLSI circuits damage the chips under test as it generates excessive heat. This is because a power saving system mode only activates few modules at the same time, whereas many nodes switching occurs at test pattern. Also, the switching activity increases between test vectors during testing. The power dissipation in CMOS circuit is mainly due to two main reasons. First is static power dissipation, due to the leakage current and other currents drawn from the supply power. And second is the dynamic power dissipation, due to the charging and discharging of load capacitance and switching transient circuit. The dynamic power dissipation is the main source of dissipation and consumption. The total energy consumed in the circuit during application of the complete test sequence is given as follows, where E is the total energy is equal to half into CO, that is the load capacitance, into VDD, that is the power supply voltage, summation, where SWI is the number of switching provoked by the test vector Tk at node I during the test period T. CO and VDD are constant, only switching varies. So the total number of transition is given as the estimation power of power consumption during test. To have full fault coverage and less power consumption, weighted sum genetic algorithm based on ATPG is proposed. This algorithm works in two parts. In first part, pseudo-random process generates population sequence and test vectors. In second part, genetic algorithm is used. The fitness function is as follows. Fitness is equal to W1 into NFI plus W2 into NTR, where NFI is the number of faults detected, NTR is the number of transitions, and W1 and W2 are weights. The upside of this methodology is high fault coverage and consumes less power. On the downside, it is not efficient in handling mixed optimization problem. Problem with the WSGA non-dominant genetic algorithm is proposed. Two methods mainly differs NSGA from WSGA. First is non-dominant sorting. Over here, to classify the entire population into different non-domination fonts. Second is crowding distance assignment. Its computation requires sorting of the population. The sorting algorithm governs the complexity of the computation. The selection process at the various stages of the algorithm to perform a uniformly spread out font is done by crowded selection operator, which is pi. Every individual in the population has two properties. First, non-dominant rank given by I rank and crowding distance, which is J distance. The J distance is given by I pi J if I rank is less than J rank or I rank into J rank, and I distance is greater than J distance. Further, NSGA uses an elite preserving operator which makes possible to pass a best solution of the particular generation to the next generation without being affected. As in genetic algorithm, there is a probability for the best solution being affected. NSGA2 based ATPG is divided into two phases. In first phase, to generate the initial population of the test sequence, pseudo-random process is adopted. If the fault is detected in sequence, that sequence is added to the set, further given as input to the second phase. In the second phase, using selection, crossover, and mutation operators on population obtained from the first phase child population is developed. Further, NSGA2 procedure is applied to the parent and child population combined. The test sequence is added to the test set after detecting the faults and removing them from the fault list. Next sequence have the remaining faults from the fault list. The fitness function used in NSGA2 based ATPG is Fi is equal to NFi minus FCI, where Fi is equal to Pi. NFi is the number of faults that is given to the ith test sequence. FCI is the number of faults covered by the test sequence, and Pi is the number of transitions during the application of the ith test sequence. The upside of this methodology is it provides better coverage, but on the other hand, it consumes high power. In order to overcome the problem with NSGA2 based ATPG, redundancy is added. By adding redundancy, it selects better test sequence in the first place, which will minimize the number of transitions during test pattern generation, thus reducing the switching power. This is achieved by using elitism property, which selects only n better solution out of 2 raised to n solution, which are further processed using genetic algorithm operators, thus retaining the best sequence till the end of the operation. Redundancy modifies the fault dropping phase, where a fault is dropped only if it is covered by at least m sequences, where m is the redundancy factor. NSGA2 based ATPG with redundancy selects best test sequence, which will help to find faults while consuming less dynamic power of the unit under test. Further, these are some of the references which I have used in the PowerPoint presentation. Thank you for your time.